What's up, dude? Alright, so check this out. This rig right here is what we need to build to generate our high voltage plasma. It's a tube style circuit. Nice big variac. And this is what we're going to get right here. Listen to this thing. So this right here, this plasma flame, can totally be harnessed and controlled via wind and via pulsed lasering. So we got to build this first. That's one of the things we got to build. We also got to build a musical Tesla coil, similar to this one right here. So this is Eastern Voltage Research. It's a company that I found in, I think it's New Jersey, but they have full sets of schematics, full detailed plans on how to build a dual resonant solid state musical Tesla coil. For $45, you can get the entire blueprints and the entire technical support when it comes to building this thing. And this is designed to produce 12 to 15 foot arcs. Perfect for the warp drive system. Perfect.
However, I should add that this system is going to be a little bit expensive to build. I'm not sure how much, but I'm thinking somewhere in the $1,000 range for all the components, maybe even a little bit more. So I found another source to be able to build the exact same thing, just a little more lower powered. So this is Lab Coats, the channel Lab Coats, and he's a relatively new channel, but he has a really cool build here that is pretty badass, and he puts his videos together really well too, and he collaborates with several other channels on this topic of plasma or Tesla coils, whatever. And this is a really cool instructable video on how to build a really badass, for cheap, Tesla coil.
Today, we're building a real solid-state Tesla coil and even giving away a few of his PCBs. Let's go.
See, that was a badass intro. Nice and quick, a lot of fast changing scenes with some fast music. It gives you a really short, badass intro. And he's got these broken down. What we're building, circuit overview. That's a good overview of the circuit right there. That's basically it right there. Minus the part with the X on it. I'll have to show you what I got. Oops. I'm trying to take a screenshot of that. Anyways, trying to find it here. This uses an antenna to switch this thing. These down here are antennas that he'll show you.
I additionally changed and removed a few other components, including the undervoltage protection part of the circuit, after I found it was causing more harm than good. Also, to make assembling this coil easier and less error-prone, I designed a compact PCB for it using the free Easy EDA online editor. I ordered the PCBs from jlcpcb.com.
I have the file also, and order these.
But I might have gotten a few extras. Stick around to the end of the video to see how you can get one. The driver for this coil works by first extracting a crude feedback signal from an antenna near the coil and passing it by a 2-diode array. As Paramax demonstrated to me over a Zoom call, these 2 diodes essentially lock the positive and negative voltage peaks of the AC signal to a set value, preventing dangerously high voltages from entering the sensitive driver circuit. Next, the signal passes through a resistor, capacitor, and 74HC14 Schmidt trigger, which converts a somewhat sloppy signal into a more functional square wave that matches the resonant frequency. The new square wave signal is then pumped into the UCC27425 gate driver IC, where it is amplified. Conveniently, our gate driver chip has something called an enable pin, which is basically like its on and off switch. If we feed the interrupter signal to the enable pins, we can control a Tesla coil's pulse duration and frequency, and therefore the spark appearance. By the way, all of this low voltage circuitry is powered by a few simple voltage regulators, which take any DC voltage from 14 to 24 volts and adjust it to fit the circuit's needs. The resulting interrupt signal from our driver circuit is finally sent to a small device known as a gate drive transformer, or GDT. The GDT can be easily made by wrapping 2 12-turn coils and 1 8-turn coil onto a suitable ferrite core. There are plenty of usable ferrite cores out there, but the ones I recommend are made of materials 77 and 75. I'm personally using a number 77 ferrite in my design. Once properly assembled, the GDT converts the single 12-volt signal from our driver into 2 18-volt signals, which are optimal for switching our transistors. If we phase the GDT correctly, it will cause the transistors to switch the DC voltage from our power supply across the primary coil at the resonant frequency. And since the resonant frequency is detected by the drive circuit, we can stick basically any secondary coil in the primary coil's field and it will resonate almost perfectly, producing an extremely powerful electrical discharge. Now, our circuit is designed to run with 340 volts DC.
That's awesome. It can be used with any Tesla coil, no matter what size your secondary is. It'll still work. It's pretty awesome circuit.
Most wall sockets tend to only output 120 volts AC or 240 volts AC, depending on where you live. So, how do we get that kind of voltage? I'll let Clayton from the Plasma Prince explain.
Hey everyone, I'm the Plasma Prince, and I designed the doubler PCB. It's pretty simple. I mean, it's just your typical voltage doubler, but in 240 volt countries, it's just a full bridge rectifier. Or more commonly known as
Full bridge rectifier.
the NTC thermistor will soft start the whole circuit, so current goes in a little bit slowly than it would without, and that's overall better for the circuit. Then it goes through the diodes and gets rectified, which converts 120 volts AC to 170 volts DC, half wave, that is. So the current almost behaves as if it's pulsated, and we don't really want that for the circuit. Plus, 170 volts DC isn't as great as what we could go to. So we have the big rectifying caps at the end that smooth out the current and also allow the voltage doubling phenomenon to take place. These big capacitors will charge in parallel and discharge in series, which allows the voltage to sum up to 340 volts DC, not half wave. And that's exactly what we want to drive the bridge.
Awesome. Now that we've covered the circuit's design and layout, let's put it all together.
I recommend that we go with some different transistors, though, rated for some higher voltage. That way we can pump more voltage through it. small circuit, which that's good. It doesn't have to be huge. I mean, we can make this thing more powerful too. Like I said, changing out the IGBTs, we can drive 1200 volts through these. I've found 1200 volt IGBTs, so.
Alright, this thing's looking pretty slick, but there are still a few final arrangements that need to be made before we can fire the circuit up. For one, we actually need the coils themselves. Coil winding and setup can be a little confusing for some beginners, so I enlisted Nick from Coil Labs to help show how it's done.
When I want to build and test the coil, usually the first thing I do before I start building anything is I needed to keep it to the top load. Once you get your second, you can still speed up the process. People use primary goes through the cross section of the secondary.
Anyways, that's a whole bunch of stuff on how to build the coils. I'll take care of all of that. Let me just show you this thing in action before we go here.
Let's see what it can really do. Can you see why I love this thing?
That's with a different type of an electrode. Sodium chloride.
Alright, can you see why I love this thing? It is so much more powerful and versatile than the SSTC that we built in my last video. This circuit can even hold its own against commercial DR SSTCs. When built right, this thing can...
Did you see that? That was a pancake Tesla coil.
It is so much more powerful and versatile than the SSTC that we built in my last video. This circuit can...
That is a plasma speaker. A pancake musical Tesla coil.
even
Look at that. That is sick, isn't it?
hold its own against commercial DR SSTCs. When built right, this thing can produce sparks longer than some of the 1 Tesla coils, all while being only a fraction of the cost and less electrically stressed than a DR SSTC. And, unlike most dual resonant and spark gap Tesla coils, this SSTC circuit can drive almost any coil setup without hours of painstaking tuning. I didn't even have to get a scope to get this thing working on the first try. Of course, there's probably still one feature you've been dying to see: the music mode. On the PCB, I added a designated port to feed pulse DC signals into. If we switch off the interrupter and apply a 6 to 12 volt music signal, the coil comes to life and plays the desired tune. Have I convinced you to make one of your own yet? If you would like to make your own copy of this circuit, I put everything you need down in the video description. I put the instructions, parts list, and even the Gerber files to print your own PCB copies. To order your own PCBs, just go to your favorite PCB manufacturing site, I recommend JLC PCB, and submit the Gerber files I provided, and pay literally like $10. It's that simple. Heck, you can even pick your PCB color if you want. We're nearing the end of the video, so you know what that means. It's giveaway time.
So this is Lab Coats, the channel Lab Coats, and he's a relatively new channel, but he has a really cool build here. So that was the end of the collection of videos that I put together for you here. this is the first steps we need to take. Let me know what you think. Give me your feedback and your comments and all that good stuff. And I'll talk to you soon. Peace.